Guys, Mr. Bowman here. This is the first excellence video for 1.6 geometry, and we're focusing on all the 2017 excellence questions. So, question number 1 from the website: circles can be drawn inside a half hexagram. So we've got the full hexagram here, we've got the half hexagram there. Point A, B, and C are the centers of these circles. So we've got A, B, and C. The radius of this is, or the radius of all the circles are r centimeters, and we've got that drawn here, so we know that length as r. And we've got triangle ABD, which is over here. That's been drawn across 2 of the circles. Our job is to calculate length x in terms of r. So what that means is we need to do x equals some kind of algebraic expression where r is the subject of that expression. We're now going to look at the actual triangle itself. There we go. We've been asked to find length AD, which is x, which is this one over here. So we need to figure out something about dB. And I should note that's the radius of a circle, and we've been told that's r. And we also need to figure something out about AB. And you should have a look. That's actually r, because that's a radius. That's another radius. So combined, that side of the triangle is 2r. Because I have 2 sides of my right angle triangle, I can use Pythagoras' theory to find out the other side. And I like all the letters I've got because I've only got x and r, and that's what we've been asked to find out. So let's start by jotting down Pythagoras' theory. A squared plus b squared is equal to c squared. I'm now going to substitute what I know. So I know the smaller sides of the triangle are over here. So let's make that x squared plus r squared. And the hypotenuse, the long side, is 2r, and that's going to be squared. I should note, don't do 2r squared. That's definitely wrong, because the squared also needs to hit the 2, so make sure you put that in a bracket. So that they're definitely wrong. We're now going to focus on expanding this indice over here. So x squared plus r squared, that's unchanged. That's going to become 4, which is the 2 squared. We're then going to do the r squared as well. Our next job is to get the x by itself, so I'm going to get rid of this r squared. So I'm going to go minus r squared minus r squared. So that means x squared will be equal to 3r squared. Finally, I'm going to square root both sides to get rid of that square by the x. So x will be equal to the square root of 3r squared. If you got that line of working, that's probably enough to get your excellence mark, but we can simplify that a little bit more. Let's make that the square root of 3 times r. We are now on to question number 2 from the website. In the diagram below, line SR is a tangent to the circle, so that's going along there. Line BT passes through O, which is the center of the circle, so that there is line BT. That represents a diameter, or 2 radii. Prove that angle AB equals angle AQB. So we're trying to show that ABS is equal to AQB. So this question here, in all honesty, when I first looked at it, probably the only excellence question, I just couldn't figure it out, so I had to work back from the answers, but hopefully my explanation kind of gives it justice. So the first step we needed to look at was this perpendicular nature of the radius and the tangent. So we know both of these here are 90 degrees, and the one on the left, if we have this angle here, we know that this angle and this angle, they have to add up to 90 because they're between the tangent and the radius. So my first step, I know that angle ABS is equal to angle ABT. Oh gosh, sorry, that shouldn't be equals. That should be them plussing together equals 90 degrees. And that was that tangent rule that we've looked at. So tangent to the radius or radii, they are always equal to 90 degrees. So that was our first step. The next step we know is if I make that angle there, this here is going to be a right angle because BT is the diameter and that's the angle at the circumference. So that's the semicircle rule. So the next thing I know is I know that angle BAT, I know that's equal to 90 degrees. And the angles in a semicircle equal 90-degree rule. Because I know this angle here is 90 degrees, I know that the remaining two angles in the triangle, they have to add up to 90 degrees because of that triangle rule. So from that, I know that angle ATB plus angle ABT, they were the two angles that I've circled. I'll put dots in over there. Plus that 90-degree angle we identified before, that has to equal 180 degrees. And if I simplify that, I know that angle ATB plus angle ABT, if I did minus 90, that there has to come, or those two combined have to come to 90 degrees. And I've used that internal angles of a triangle rule. Internal angles of triangle equals 180 degrees. And hopefully you can see what we're doing here, but we've got an ATB over here, or ABT, and we've got ABT over here. So we're forming expressions in terms of A, B, and T. We're going to carry on with that theme. So from the first line here, I'm going to do a little bit of algebra. So I'm going to go minus ABT minus angle ABT. And I'll show you what that gets us to. So angle ABS, that will be equal to 90 degrees minus angle ABT. And I'm liking that because if you have a look at the other line of working here, we've got 90 and ABT. So I'm actually going to do the same thing there, and that means those would be similar expressions. So let's go over here. So I'm going to go minus angle ABT minus angle ABT. So that means angle ATB will be equal to 90 degrees minus angle ABT. Now we've got the same expression coming up twice, 90 degrees minus ABT. So that means these two angles here are going to be the same. So this tells us, so from these two here, I know that angle ABS is equal to angle ATB. Back, that means this angle up the top, which is ATB, is going to be equal to this angle down the bottom, which is ABS. That's what this here is saying, or telling us. Next thing we need to look at is we've thoroughly looked at this ABS stuff. So just want to focus on ABQ a little bit, which is the second half of what we're trying to get to. And I've changed Painkiller just to help us out. So I know angle ATB. And I just thought I'd note that's sitting on the same arc as angle AQB. And that's how we're going to make the connection here. So I know that angle ATB, that's going to be equal to angle AQB. And that's because they are angles on the same arc. So angles, same arc, are equal to each other. And that's the final piece of the puzzle. So this here is telling us ABS, so moving over here, angle ABS is equal to angle ATB. That's the first thing, which is also equal to angle ABQ. And if we ignore that middle one, we've got ABS is equal to ABQ. So therefore, angle ABS is equal to angle ABQ. And that there wraps up our answer. So if you get to that, that there is where your E would be. So just want to emphasize this question here, really, really challenging. Probably, if I sat this exam, probably wouldn't have got that question, would have been comfortable with the other ones, but that one was a bit of a headache, a very hard proof question. Okay, we are now on to question number 3 from the website. You'll be glad to know this one's a bit easier than that headache question 2. But let's get into it. I should note before we actually do, there was several different ways to get to the solution. This was just one way I got. By chance, it was the same as the answers, but different ways will get different answers. So what I'm going to do is I'm going to start off with looking at this angle here. And that angle there, so angle PDE E, that there is going to be equal to 180 degrees minus Z, and that's because angles on a straight line, they combine to get 180 degrees. After that, I've moved down here to angle DCB. I also know that angle DCB, that's equal to the same thing, 180 minus Z, and it could have been because it's co-interior to Z, or it could have been because it's corresponding to angle PDE. I'm going to use the corresponding angle rule. So corresponding angles in parallel lines are equal to each other. Okay, so I'm now going to move up to the top of my diagram, a bit of a headache, but I can figure out this angle here because it is vertically opposite. So I know that angle API, that's going to be equal to angle JPK, which is equal to Y, and that's because vertically opposite angles, they are equal to each other. Now that I have that angle, I can form an expression for that angle in the middle because they're sitting on a straight line. So angle DPE, which is sitting over here, that there is equal to 180 degrees minus 47 minus Y. That gets me to 133 minus Y, and I've used angles on a straight line equals 180 degree rule to get that. Now getting closer to what I need to do is, because I'm trying to find out angle X, which is sitting down here, and angle X is going to be corresponding to this angle here. And if you have a look, they're all sitting in a triangle. So I've got two of these sides, which means I can go 180 minus these two to find out this angle here. So let's get into that. So angle PED will be equal to 180 minus this angle over here. And I'm going to put that in brackets, minus 133 minus Y. And then I'm taking away the very first angle I've calculated up the top there. And that's minus 180 minus Z. Bit of simplifying to do here, but I know this 180 is going to be cancelled out by this 180. We're going to have Y, because we've got negative times negative. And then we're going to have negative times negative here. So plus Z, and that's going to become negative 133. And the final step is I'm now going to go down because it's corresponding. So X is equal to angle EBC, which is equal to angle PED, which is equal to Y plus Z plus 133. And that's because corresponding angles in parallel lines are equal. I thought a fairly straightforward excellence question. Nothing particularly complicated there. Hopefully you're confident forming expressions throughout your geometry questions. We are now up to question number 4 from the website. Let's run through the question quickly. ABC is a triangle in a circle. O is the center of the circle. We can see that there. PE is a tangent to the circle at point A, and we've been trying to prove that angle X is equal to angle Y. I suppose the first thing to note, this center, it's a weird comment because nothing goes through the center of the circle, so it probably suggests that we're probably going to need to construct something. So we might need to add in some radii somewhere to help us out with this question. So the first thing we're going to do is we're going to start off by adding this AO line. So AO is the radius of our circle, which means angle DAO, that's going to be equal to 90 degrees because of that tangent to the radius rule. So tangent to radius equals 90 degrees. From that, I'm going to form an expression for the angle sitting in the middle there. That's angle BAO. Angle BAO, that's going to be equal to 90 degrees minus X, and that's the same reasoning as above. So that's our first step. My second step, I'm actually going to form another radius, BO. So BO, that's also going to be the radius of our circle. And I like this because these two lengths are the exact same, which means we're dealing with an isosceles triangle. So that means triangle AOB is an isosceles triangle. So that means that base angle there is going to be the same. So angle ABO will be equal to angle BAO, which is equal to 90 degrees minus x. And that's because angles, or base angles, I should be more specific, base angles in isosceles triangle are equal to each other. Okay, now that I've got that, I'm going to move up and I'm going to work to the top of the circle here, top of that triangle near the circle center. So they are all in a triangle, so we're going to use subtraction. So angle AOB is equal to 180 degrees minus those two angles we found on the base. So minus 90 minus x minus another one of those. So the 90s are all going to cancel each other out, and we're going to have negative x and negative x. That becomes plus x, which becomes 2x. So we're nearly there. That angle in the middle is 2x, and that's the angle at the center of a circle, and this is an angle at the circumference of the circle. So I know the angle at the circumference is going to be half of that. So angle ACB, which is equal to angle Y, I should have noted, that's going to be equal to 2x divided by 2, which is equal to x. And my rule, this is the annoying one, there's no short way to do this, but angles at center 2 times angles at circumference. And then that's our proof. Therefore, we've shown that x is equal to y, or vice versa. Okay, we are now up to question number 5 from the website. Got a whole lot of information here. You might have seen this diagram from the previous questions as well. But we've got 2 overlapping circles, so that's those over there. And they've got the centers A and B. And they are drawn in a quadrilateral which is symmetrical through H3. So that's a quadrilateral there, and it's symmetrical down the middle. We've been told that HIGI is a rhombus, so that might help later on. HI, basically all the sides here, they are all tangents to the circle. I've been given information about that 38-degree angle down the bottom there, and I've got some information about AD being perpendicular to those ones there. We've been asked to calculate the size of angle Y. So when it says size, it means you actually need to come up with a number. That's different to a lot of the other excellent questions we've looked at in this video, and angle Y is up there. Just to help us out, I've got a bigger diagram floating around, and I think this will be a good first step there. So the first thing I've noticed is I need to kind of work through this way and get to Y is basically what we're working towards. I'm going to start off with this angle down the bottom here, and that's because we've got a radius here and we've got a tangent floating around there. So I know that 90 degrees has to be angle BEG. So let's get that in. Angle BEG is equal to 90 degrees, and that's because of that tangent rule. Tangent to radius is equal to 90 degrees. Do forgive me as I am writing a bit smaller than the previous videos just to get some room in there. From that, we can figure out angle, the small angle in the middle there. Angle BEC, that's going to be 90 minus 38, and that there is going to get us to 52 degrees. And our reasoning, we're really relying on what we did above to get to that. I can now figure out this angle over here, angle X. So I've got I suppose I should start by calling it x, but x is equal to angle BCE, which is equal to 52 degrees as well, and we're using our base angle rule. Base angles of isosceles triangle are equal to each other. Okay, so I've now got this angle here, and I've got 2 of the 3 angles in a triangle. I may as well go the extra step to find out that top angle there. So angle CBE is going to be equal to 180 minus 52 minus 52. That's 180 minus 104. So I'm getting 76 degrees there. And that's my angles in a triangle rule. So internal angles in triangle equal 180 degrees. Now, this step here is where it gets a bit messy. What I'm going to do is we're going to need to get into a bit of construction. And if I connect F to C, I've got that line there. And I've changed pen colors just to show you a little bit better, but this point and this point here, and we've got that arc floating around here. So that means this triangle here is on the same arc as the smaller triangle here. So we're going to use the twice at the center rule to get us to this angle up the top here. But that's not all of y, which is going to be the issue. So let's get into that. So angle CFE is going to be equal to 76 divided by 2, which is 38 degrees. And our reasoning, angles at the center are 2 times the angles at the circumference. So forgive my poor spelling and poor writing for that last part. Just cleared a bit of working here. And you can kind of see down there that we've got this angle here, which is going to be 1/2 of y. And we've got the other half of y. So what we need to do is we need to double this to find all of y. So y, which is equal to angle DFE, is going to be equal to 2 times 1/2 of y, which makes sense, which is equal to y. So that's going to be 2 times, I suppose I should be specific, 2 times angle CFE, and that's what we calculated above. And that there is equal to 2 times 38, which is equal to 76 degrees. So we're back up to here. So that angle ended up being equal to that angle there. And the reason really we're doing here, basically it's just that symmetrical nature of the shape is how we can get to 76 degrees there. So we found out angle Y, or DFE, is equal to 76 degrees. Our final question for this video, question number 6. We've got a kite, which is this shape over here. So kites have that symmetrical nature in it. We've also been told that side, or line DG is equal to GB, which is equal to EC. So what that's trying to say is these two angles, or angled lines, they are equal to the sides of these squares. So that information is really important to process this question. The last step is we've been asked to calculate size, the angle of size x, so we need the exact value to get to that. Okay, so first thing to do with this question was this one here. So this side is equal to this side. So we're thinking isosceles triangle, but there's a bit of a trick. If I drew a line connecting here, this line is equal to the dimensions of the square, which is the same as this side and this side. So all 3 sides are the exact same. So that means that triangle is an isosceles triangle, or sorry, an equilateral triangle. So triangle DEG is equal to an equilateral triangle. And what that tells us about all the internal angles, they're all going to be 60 degrees. So let's get through listing them. Angle DEG, which is this top angle here, that there is equal to the bottom angle down here, which is angle EGD, which is equal to this angle here, which is EDG, which are all equal to 60 degrees. And that's because angles in an equilateral triangle, they all equal 60 degrees. What we're going to do next is, because we know the shape is symmetrical, I'm going to chop my shape in half. So I'm going to chop it here, and I'm going to start investigating this shape, this purple triangle here. And I know this one at the bottom, that's going to be 30 degrees. It's half of 60, and that's due to the symmetrical nature of what we've got going on. So angle BGD, that's equal to 30 degrees. And my reasoning, really just symmetry is how I got to that. This next part's quite annoying to see just from the shape, but just a reminder, this side here is equal to the sides of the square, which is equal to this side here. So that means these two base angles, they are going to be the exact same. And I like that because this base angle here is going to be half of the overall x value. So let's find out those two base angles sitting in here and here. So we've got angle DBG, which is just the one by the x that we're focusing on. That there is going to be equal to 180 minus 30, which 30 is that smaller angle up the top there. And we're going to divide it by 2 because the base angles are the same. So that there is 150 divided by 2, which is equal to 75 degrees. And we use two rules to get that. We use the internal angle of a triangle rule. Internal angles of triangle equals 180 degrees. And I've also used the base angle equal rule to divide it by 2. So base angles of iso triangle are equal. So I've used both of those to get there. Now that I've got 1/2 of x, I'm going to multiply it by 2. So x is equal to angle DBE, which is going to be equal to 2 times angle DGB. And the reason we can do that, that's the symmetry of what we're going on here. So we're just going to add on that side there. That there is going to be 2 times 75, and that gets us to 150 degrees. And we've calculated size x. So that wraps up the excellence video. Pretty long video compared to the other ones, but hopefully seeing them go through step by step adds a lot of value compared to looking with the answers. So thanks so much for watching, guys. Keep an eye out for the next excellence videos coming out soon.